All right, question one. A 1.70 kilogram block is at rest on a rough incline. The angle of incline is 35 degrees. Draw and label the forces on the block. Determine the static friction coefficient. First force we always draw is the force of gravity. It goes down from the center of the object to the center of the earth. And the force of gravity is equal to the mass of the object, 1.70 kilograms times 9.81. I'm not going to make it negative from now on because the direction of the arrows will tell us the direction for force. And overall, if there is a net force, that should be the positive direction. In this case, the force of gravity is 16.7 newtons. We know that there is the normal force acting on the block. The normal force is what prevents the block from accelerating through the ramp. This normal force, notice how I draw it. It goes up from the bottom surface of the block. It is at a 90-degree angle with respect to the block surface. It's not out sideways. It's not in any other direction. It comes up through the center of the object, straight up, perpendicular to the surface of the ramp. Now this normal force does not equal the force of gravity, and it's because this object is on an incline of 35 degrees. So the force of gravity effectively kind of splits, if you will. The force of gravity will have a component that is also going through the surface of the ramp. It is equal in magnitude, opposite in direction to the normal force, and this component of gravity is what gives rise to the normal force. I will call this F through. This is the component of gravity that would try to push the object through the ramp, and it is equal in magnitude, opposite in direction to the normal force. Then you have a component of gravity that would try to send the block down the ramp. It is parallel to the surface of the ramp. This force is like this. I like to call this F down. It's the component of the force of gravity that would try to send the object down the ramp. F down. I'm redrawing the vector up along the surface of the ramp. Notice that it's parallel to the surface of the ramp. The reason the object is at rest is because the ramp itself exerts friction, static friction, on the block, so the block does not accelerate down, it's at rest. And this force of friction is equal in magnitude, opposite in direction to the force down. This is why the system is in equilibrium. So let's identify these forces. We have theta. I'm sorry, we're going to do these angles. Excuse me. We have this angle theta, and this angle theta is 35 degrees, and this angle is the same angle that exists between F through and FG. This theta right here. These two angles are equal to each other. So I have the force of gravity. It is the hypotenuse right now with my of this vector triangle. The force of gravity is the hypotenuse. I have an angle. The angle is 35 degrees. It's the same as the angle of incline. I have this angle right here. I have this force through the ramp. It is equal in magnitude, opposite in direction to the normal force. It happens to be the adjacent side of this vector triangle that you see here. And then I have the force down the ramp. It's the force of gravity that is split up, and it tries to send the object down parallel to the surface of the ramp. I can now determine the force of friction, force down, the force normal because of an angle and because of having the hypotenuse. So my force through the ramp, choose purple color for this. Force through the ramp is equal to the force normal. Force through is the force of gravity times cosine of the angle. The force through will be 16.7 times cosine 35 degrees. If I do this in the calculator, I make sure my calculator is in degree mode. 16.67 times cosine 35. I'm rounding here. So the force that tries to send the block through the ramp, this component of the force of gravity, is 13.679 newtons. This happens to equal force normal. So force normal is 13.7 newtons, thereabout. I'm rounding. It's equal to 16.7 times cosine 35. It is equal in magnitude, opposite in direction to the force through the ramp. Okay? The component of the force that tries to send the block down the ramp should be equal in magnitude, opposite in direction to the force of friction. So I can calculate force down, then I know my force of friction. Force down the ramp will be FD, F down, force down, is equal to the hypotenuse, in this case 16.7, times sine of 35 degrees. Force down, 16.7 times sine of 35. Force down will be equal to 16.7 times sine of 35. This is around 9.6 newtons, which means that the force of friction is also 9.6 newtons. The object is in equilibrium, it's at rest. So the force of friction matches the force down the ramp. Equal in magnitude, opposite in direction. So we need the static friction coefficient. The force of friction, clear this up, make some space. Force of friction is equal to mu times force normal. So my force of friction divided by force normal equals mu, and mu is the static friction coefficient. That's what we're ultimately looking for. So I will take this 9.6 newtons of force, I will divide by 13.7 newtons. I should have a unitless number because the static friction coefficient is unitless. 9.6 divided by 13.7. And this is a coefficient of 0.70, and I can just leave it like that. Okay, that's question 1. Question 3. A 14 kilogram block is suspended from 2 wires. The angle between the wires and the ceiling is 33 degrees. Draw and label the forces on the block. Calculate all the forces on the block. Start with the main one, force of gravity, Fg. And the force of gravity is equal to 14 kilograms times 9.81. 14 times 9.81 is 137.3. I'm just going to round this right now, 137 newtons. All right, so we have 2 strings and they are at an angle. They exert tension. So I'm going to label this tension, tension. The vertical components of these 2 strings, of the 2 tension forces, will equal the total weight of the object. So I'm calling this Ty, Ty. That's for the vertical component of the tension forces. So Ty plus Ty should equal 137 newtons. Each of these strings bears some of the load. They each bear some of the load or the weight of this block. So if I combine, this is 2 Ty equals 137 newtons. So the vertical component of the tension is 137 over 2. That happens to be 68.5 newtons. All right, now we're ready to get our hypotenuse, or the the total tension in the wires. Because we have, for example, our T is unknown, that's the total tension, but I now know the vertical component of one of the tensions. This Ty is 68.5, and I have an angle right here. The angle was given as 33 degrees. So this is an adjacent side, this is a hypotenuse, I have an angle. Cosine of this angle will equal the adjacent side, 68.5 over tension. So my total tension, let me change colors, sorry. The total tension will equal 68.5 divided by cosine 33 degrees. All right, so the tension in each of the wires, then if I do 68.5 over cosine 33 degrees, total tension in each wire is around 81.67, 81.7 newtons. All right, I hope you found this video helpful. Thanks for watching. Study well.